Okay, so today we're still talking about transforming your data with for simple linear regression. Okay, so just recap. We talked about inference in week 1, review of that, and I hope that was okay for all of you guys. I hope you guys are all caught up with your understanding of inference. And then we introduced simple linear regression, fitting all of that, making inference from models. What is the point of regression? This is here. Sometimes we lose sight of the big picture. Why are we studying regression in the first place? What are we doing in this class? Anybody? Okay, well, I will answer my own questions. What's that? Yeah, we're trying to explore relationships between variables in our data, okay? And we have two primary purposes or uses with regression. And what are those? Okay, one is making predictions. Okay, so that's probably the most common use for regression today, is making predictions. And then the other one is sometimes when we find a regression model, it gives us an understanding of the underlying process that exists. So maybe from some scientific perspective, it helps us understand what's happening at some, process level. Okay? But anyway, all of that is only valid. Our predictions and our understandings and our interpretations are only valid if the model is valid. Okay? They're only good if the model is a good representation of reality. Okay? And so we have model diagnostics to kind of make sure that the assumptions we're using haven't been violated. We covered transformations to kind of correct problems of non-constant variance. And so this week we're going to use transforming data to fix more problems. Problems of non-linearity specifically. We'll also look at weighted least squares this week to also fix other problems of non-constant variance. We'll see. Okay, so on Friday we talked about applying the square root transform to fit our data, and we said we can take the square root of our y observations and the square root of the x values and fit a model there. And another option that we can do is we can take the log of all of our y values and the log of all of our x values. Okay, and so the log transform just works very similarly in that you just apply this transformation and then you fit a linear model between the transformed x and the transformed y, and then you see if it works. Okay, and so just like before, you've got to check your standardized residual plot to make sure you're not violating assumptions of non-constant variance. You need to check your scale location plot also to make sure you're not violating your assumptions of non-constant variance and other stuff. So let's try that. Let's go back to the cleaning data. Okay, and so so I'm just going to briefly talk about the code here. Okay, so this is just to download the code, and I'm hoping all of these R commands are working fine when you run them on your own computer. Somebody commented that they get errors, so you might have to install a library called downloader. So downloader, so it's download ER, like, I don't know, someone who downloads, and then you would change this function from download.file to just download. Okay, and sometimes that solves problems. No guarantees, but if you're having trouble, just let me know. Okay, and then and I'm creating transformed data using dplyr's mutate function, which I think just makes it really easy. We just take the cleaning data and we're going to create 4 new columns: square root x, square root y, log x, log y. Okay? And now I'm fitting 4 linear models. The original cleaning model between rooms and crews, the square root cleaning model between square root y and square root x, and then the log cleaning model between log y and log x. Okay, so far so good? Okay, so that's it. And then let's take a look at each of these. So this is the original data. We fit the linear model. We plot it using ggplot. This is their command. And we see, oh yeah, you know, it looks like it's trumpeting out. Okay, we take a look at the standardized residual plots. Also, we see the trumpet phenomena, which we don't want here. Okay, sign of non-constant variance. And then the scale location plot, there's an angle here, so this is a bad sign. Okay. Here, this is our square root transform. We square root x, square root y. This is what our data looks like now. Okay, that looks pretty good. The standardized residual plot also looks pretty good here, in that the variance seems to be fairly constant. And the scale location plot, this line appears pretty flat. So these are all good signs for the square root transform. All right, let's try the log transform. Okay, so we apply the log transform to x and log transform to y. Okay, does that seem good? Yes, no? Maybe. It's hard to tell. It's hard to tell, but it doesn't seem so great. Okay, what about our standardized residual plot? Does this look good or bad? So it looks like it actually kind of trumpets the other way. It's like it overdid the shrinking of the big residuals out here. Okay, and then when we look at the scale location plot, we see now we have a downward angle here. Okay, and so this would indicate that the log transform, taking the log of x and the log of y, probably is not the best. Okay, and so just if we shopped around looking at these different things, we would come to the conclusion that the square root transform seems to be the appropriate transformation to apply to our data. Okay, and so I think, you know, last week there was some questions like, how do we know which transform to use, or, you know, do we run the risk of overfitting or like kind of overdoing it? And the answer is, yeah, you know, there's always these problems, okay, and so, or possibilities. And so what you want to do is, if your model seems like it's a good fit to begin with, like if your original data seems okay, don't bother fixing it, okay? But here when we look at the original data, we see problems of non-constant variance. So then that indicates to us, hey, we should try something to try to fix this problem because we don't want non-constant variance, okay? And so, you know, we did the square root transform and that worked. You could try out the log transform to see how that goes. And it turns out that it wasn't better than the square root transform. So we would decide on the square root transform. I wrote, it bears repeating that fitting regression models and transforming data is not an exact science. There are some guidelines that exist in terms of when you would want to use the square root, when you would want to use the log transform. But the truth of the matter is generally we don't have a very clear understanding of the underlying process of what's generating the data, so we might not know which one would be better to use, the square root or the log. And in terms of work necessary, it's not very difficult to fit a linear model for log transform data and square root data and do a comparison. So it's totally fine to try a few different methods, see which one works best, and use that, okay? You know, there's one thing that we, you know, didn't do, which you could do, is you can take all of your x values or y values and subtract them from a constant so that it kind of changes the order this way to that way, and that can help. And yeah, it's here. It says it's entirely possible that different statisticians will look at the same data and create different models. That it's just, you know, this is not mathematics. Mathematics, like, things are very like following the orders of logic, and so you have one thing. With statistics, you're dealing with real life data, so it's not so clear. And again, so keep in mind the two major purposes of regression: to provide insight into the actual relationship between variables and to make predictions. So if your model is used to provide scientific insight, then the transformations that you use could have significant meaning on the understanding of the underlying relationship, okay? And so if that were the case, you probably want to stick with fairly easy to understand transformations, okay? But if you're using your model for predictive purposes, then it doesn't really matter. I mean, it's not as important, okay? You just want a model that's got good predictive properties, meaning, you know, constant variance and all of that stuff, fitting the assumptions correctly. But square root transform, log transform, I don't think people really care, okay? If you can make good predictions, we're happy. Is that okay? And I posted a small little handout on CCLE in last week's module, just about this data transformation business, because I know it might feel a little uneasy in that we just have this kind of loosey-goosey interpretation or method for it. So one thing that's really nice about the log transform is that it does have a practical interpretation. Okay, so normally when you just fit simple linear regression, you can interpret the slope, and the slope goes something along the lines of, if we increase x by 1, we expect y, our prediction for y changes by the slope. Okay, so we change the slope, change our prediction for y by b1 or beta 1. That works nicely. When you're dealing with transformed data, like the square root of x and the square root of y, then it means adding 1 to the square root of x is accompanied by this change in the square root of y. But what does that even mean, right? Like adding an extra square root, you know, adding 1 to the square root of cruise increases the square root of the rooms cleaned by this. It's hard to interpret that, okay? So usually you just talk about how your predictions have changed. But with the log transform, because sums of logs are products, we can then say a 1% increase in x is accompanied by a beta 1% change for y. Okay? This is technically not 100% true in that this is only true as long as beta 1 is relatively small. But overall, this is a pretty good understanding. Changing x by 1% will translate to a change of y by beta 1%. So you do have a nice interpretation of the slope for the log transform. Okay. And that's how we did all of our calculations back in the day. I guess not we, but has anyone used a slide rule? Ever? Have you guys seen one? Do you even know what I'm talking about? No. Oh man, okay. History lesson. All right, let's talk about slide rule. So before the days of calculators, this is what you had, because you didn't have calculators, and like, so for the Apollo missions, like to get people to the moon, they would do their number crunching using this thing, okay? And this middle piece slides back and forth, and you would use this fine little line, and you'd line up your numbers, and you'd put like, see, you would line this up at like 5, and then you'd slide this over, and then you go over to 3, and then when you look at the number over here, it says 15, okay? And you can do all sorts of stuff with the slide rule. Look it up on YouTube, like how to use a slide rule, and I think you'll be impressed that like people did math this way, okay? And it works because of logs, right? When you add logs together, it's products, and that's basically the principle with the slide rule. So anyway, yeah, that's how we got to the moon. I mean, there were some computers, but yeah, okay. All right, so now we can talk about transformations to address problems of nonlinearity, okay? Sometimes only the y needs to be transformed. Sometimes only the x needs to be transformed. Sometimes both x and y need to be transformed. And I only finished the slides for only y need to be transformed, but we'll see how far we get and maybe what I can talk about without the slides. Okay, so what if y was not linearly related to x, but was equal to g of this linear relationship, okay? So basically g is some unknown function, and so we might have simple linear regression in the form of g inverse of y is equal to, you know, beta 0 plus beta 1x plus some error e, okay? And if this is the case, then you know, this isn't too terrible, but it's just trying to figure out what is the inverse function of g, okay? And so for this, we're going to just demonstrate how this works, and we're going to say the true relationship in the population is that y is related to x, and we're cubing this thing, okay? So this is the true relationship, but it's being cubed here. Okay, and so if we just try to fit a linear model to this, what is it going to look like? It's going to look like this, okay? So this is our linear model, and we see it's not very good. Okay, so if you look at this and you're like, oh yeah, that's good enough, then I have failed at teaching you. Okay. So anyway, okay, so we look at the standardized residuals, and we're like, oh yeah, there's definitely a pattern here. Okay. So this is an issue, right? We see the non-constant variance, the variance increasing, and then there's clearly a U, okay? And then when you look at the scale location plot, we're like, oh yeah, this definitely doesn't seem quite right either, okay? It looks like this because we're taking the absolute values of the standardized residuals, so it bounces like that. That's kind of cool though. Okay, so our plot reveals some serious deficiencies in using the linear model, and so we might consider transforming y or x or both, okay? And so to help us decide, we're going to look at the distribution of x and the distribution of y and determine which variable should be transformed, okay? So if we look at, here's the QQ plot of y and a histogram of y, and we look at the QQ plot of x and a histogram of x, okay? It looks like x is kind of normalish, x kind of is symmetric, whereas y, there's definitely skew, okay? And we notice that also in our QQ plot, that this is not a straight line. So in this case, we're going to work on just transforming y, okay? All right, so we're going to look at this class of power transformations, okay? So, oh yeah, histograms of x and the QQ, histograms and QQ plots say y is skewed, but x is not, so we'll transform y. So these are power transforms, and these are called scaled power transformations. of strictly positive y. So it requires that y be positive, and maybe that means you've got to add a constant to your y to get everything positive. Okay, but then keep that in mind when you make interpretations that you now have to then subtract that constant back at the end. Okay, and so what it is y raised to the lambda. Okay, and then we do -1 over lambda. And so essentially, really, because lambda is going to be a constant, and we're going to find a linear relationship, this part just gets canceled out as part of the linear relationship. So the only part that really matters is y raised to the lambda. So the reason why we have it in this form is because as lambda goes to 0, I don't know if you guys remember from calculus that y to the lambda -1 over lambda will turn into the log of y, that relationship. So if you do limit as lambda goes to 0, this thing turns into this thing. So that's why we have all of these extra funny things rather than just saying y to the lambda by itself. Okay, but I mean, if you think about, like, when you fit a linear model, these things just kind of get taken care of in the slope, right? Okay, so this is the scaled power transform. We use the symbol psi, and then now we fit the model based on this, and we try to minimize the residual sum of squares here. Okay, so another textbook, Weisberg, says that we can just look at different powers of lambda, okay? From -1 to 1, and we just try a few of these. And he says that's usually good enough, okay? If you want, you can try some more power transformations in between, or whatever you really want to do, and you can do that. And one way to do this would be there's a tool called inverse response plot, okay? And it's going to plot. It feels funny, but it takes the y and we plot it against the y hats. Okay, we put y hat on the vertical axis, and we're going to try different fits of lambda to this thing to see, which one minimizes the RSS. Okay, there is one assumption that has to be made, and that is x is elliptically symmetric, and this is pretty much, it's like x is normally distributed, but it's not as strong of an assumption as x. So if x is normally distributed, then x is elliptically symmetric. But you can have x that's elliptically symmetric but not necessarily normally distributed, but it's kind of the same concept, meaning if you've ever looked at a multivariate normal distribution, it kind of looks like an ellipse, and that's where it comes from. But not to worry, and we're not there's no way to know if x truly is elliptically symmetric if you just have a sample of data, right? So you just kind of look at the histogram and you say, does it look kind of normal? And you're going to be like, I guess, and then you fit it, okay? This is how data analysis works. I know it feels so terrible because I'm just like not whining, but just saying, it looks good. But that, like, when you get real data, it's always messy, and you never know what the best route to do is. But so I'm just giving you tools on helping you detect serious deficiencies. Okay, so anyway, you load a library. This should be updated to car. ALR3 will do it because it calls car as a dependency, or prerequisite or whatever. But this should say car. Okay, library car, and then you run inverse response plot model, and then here we're just saying fit lambdas between 0 and 1. Okay, and then it does it, and it says, aha, I found it. Lambda, my guess of lambda hat is 0.33, okay? And it actually spits it out here, but R doesn't, but it didn't fit on the slide. Okay, you can also force it and say, hey, I want you to try all of these different lambdas, okay? And so it tries all of these things, and it says, okay, I did it, okay? And then, and we can plot, when you run inverse response plot, you can store it as an object here. Okay, so I'm storing the results of inverse response plot, which produces the plot as what's called a side effect, and the output is a list of lambdas and RSSs. Okay, and the first one is the one that it found that minimizes it. So I'm getting rid of that one, and I'm saying, okay, let's look at everything other than the very first one that you found which minimized it, and let's plot it against the RSS, and we see indeed it gets minimized somewhere around here, okay? So the output of inverse response plot, the very first one is the lambda that it found that minimizes the residual sum of squares. Okay, and so the best lambda that it found was 0.33, meaning that y hat is y raised to the 1/3 power, which is completely expected if we knew, because we know that our data was generated from x being raised to the 3rd power, we know that y should be, the inverse of g should be that y goes to the 1/3 power. Okay. So this is one method, the inverse response plot, which fits kind of a series of lambdas to this. Okay, there's another method called the Box-Cox transform, and we're applying the Box-Cox transform. Basically applies other power transformations to it. Okay, so Box-Cox and power transforms are pretty much the same thing, except here what we're doing is we're going to use maximum likelihood estimates to figure out the best use of the best lambda, okay? And so, so over here we were minimizing our residual sum of squares. Here we're trying to fit the maximum likelihood estimates, okay? And the big idea behind a Box-Cox transform is that if y and x are both normally distributed and they have some correlation rho, then y and x are linearly related. That's some theorem, okay? That says, you know, if they have, if they're both normal, then they're going to be linearly related. And so what we're trying to do with the Box-Cox method is to transform y or x or both so that they both fit a normal distribution. Okay, and so in our case, when we looked at x, we said it looks normal enough, so we're going to leave it as such. But with y, we're going to transform it so it's no longer skewed but looks normal. Okay. It uses MLE estimates for it, okay, and so with maximum likelihood estimation, the linear regression estimates are the same as the least squares estimates. So MLE for linear regression, the way to maximize the likelihood is to minimize the sum of squares. Okay. The only thing here is that the only difference is that your estimate of the variance, okay, so with simple linear regression, when you minimize residual sum of squares, the your estimate of the variance s squared is 1 over n minus 2, whereas with MLE it becomes 1 over n. Okay. So we're going to apply a modified power transformation. So pretty much the same thing as what we had before. Lambda to the y to the lambda minus 1 over lambda, okay? The only difference is that we're going to multiply that entire thing by the geometric mean of y. Okay, so the geometric mean is you multiply them and then you raise them to the 1 over n power, or you take the nth root. So arithmetic mean is you add them up and you divide by n. Here you multiply n values of y and you take the nth root. Okay, and so again, the big idea is that when you find the right value of lambda and apply the transformation, then the transformed version of y comes from the normal distribution. All right, and so to find the best lambda, or the maximum likelihood estimate of lambda, is to, we're going to take all of our data, y sub I, replace them with the transformed version, okay, with that geometric mean and all of that junk, and then we find the max MLE estimate, okay, to find the parameters. All right, and so, oh, I don't want to. Let me turn this off here. So this is implemented nicely in the library mass. Did this go? Oh, okay, well. That's. Okay, well. The plots, only part of it show here. But you use the command boxcox, which creates plots, okay? For just the transformations of the data, you have to use a different command, bc transforms, okay? So we can look at the results, and rats, let me just show you what it looks like over here. Okay, so this is what the results look like, and so we see that so this is the likelihood function, okay, and we see that the maximum likelihood happens right around here, and so this is just a zoomed in portion going from 0.325 to 0.34, and we see, yeah, it's right around 0.333, okay, so so we can look at that, at where this exactly is. Okay, and so I'm storing the results of the boxcox transformation, and then I okay, and then and I can then call using a subset command. I'm gonna have to fix this format in the slide. I can say which value of y corresponds to the max value of y, okay? And then using that index, I'm going to find the value of x that corresponds to the value of y that gives me the maximum value of y, okay? And so it says the x that gave me that is 0.33257, okay? So pretty much 0.333, okay? But again, because of random sampling and all of that, maybe it's not exactly so. Okay, so we can then fit the transformed model. Okay, so the boxcox method and the inverse regression plot, both of these transforms seem to indicate that the appropriate power transform to apply is to raise y to the 1/3 power, which makes sense to us. Okay, And so to do that, I'm going to take our data response underscore transform, which is the original data set, and I'm just creating a new field called ty, the transform of y, which is y raised to the 1/3. Okay, so I'm using the command mutate from the package dplyr. Okay, so you guys remember that? Mutate adds additional columns to your data. And then now we just fit a linear model between transformed y and x. Okay, we can then plot it, and that looks pretty good. And if we look at the QQ plot of the standardized residuals, this looks pretty good. And looking at the scale location plot, this also looks pretty good in terms of not seeing any kind of non-constant variance or patterns in our residuals here. Okay, so I didn't finish making all of the slides. So let me talk about transforming both the x and y variable. Okay. So there is this is just your textbook, right? So there is a multivariate generalization of the Box-Cox transform. Okay, and after class I'll make sure to put this in the slides with the appropriate code and post it online, so you guys can do that. But basically, now we're going to transform both the x and the y. If we look at our if we look at the distributions of x and y, if they both seem skewed, then that will give us a good good reason to transform both. Okay, so we have plots. So this is our data here. We're looking at government salary data, okay? And what we're looking at is we're going to look at the response variable, which is in 1986 we looked at 495 job classes. Okay, so if you worked for the government, perhaps you were an accountant, or perhaps you were a secretary grade 3 or secretary grade 2 or something like that. So you have different classes of job, and then we say for that class your maximum salary could possibly be this. Okay, and then they had some consultant come in and give a score based on the job difficulty, saying like, this job anybody can do, this job requires a high amount of skill and effort, or something like that. Okay, and so we're trying to create a model that relates the salary with the score. Okay, and so if we look at the base, well, if we just blindly fit a linear model to the score and the max salary, okay, this is the relationship, okay, and so we look at this and we go, that doesn't look so good, okay, and we look at the standardized residuals and we say, well, there seems to be a problem there, okay, and this is the scale location plot, and we also see, okay, so we have issues of non-constant variance. There definitely seems to be some kind of pattern. The default settings in R uses these circles, which I don't think is the best icon to do, but I think you can still kind of see, like, yeah, there's some kind of problem here, okay? And so if we look at the distribution of x and y, here, rather than a histogram, they did a kernel density estimate, which basically takes your histogram and puts a smooth line on it. There's more complicated math involved, but basically what we can do visually with a histogram and just say, here's a smooth curve, the computer does. So we look at this and we say, okay, max salary is definitely skewed right, okay? Which makes sense, right? We're expecting a whole lot more lower paying, or just average paying jobs, and a few jobs that pay a lot, right? And then we look at the kernel density for score, we also see it's kind of skewed right. So we say, well, maybe we should apply transformations to both x and y. Okay, so you see the same reasoning go through, right? You fit a linear model and you go, oh, this didn't work out so well. And then you look at both x, the individual distributions of x and y, and you say, okay, how do we fit this? Okay, and we say, okay, well, maybe we want to transform both x and y. So, yes?
So for the standardized residual plot, do you want it to look more normal rather than like that?
Yeah, so you want to see, you kind of want to see no pattern, right? So you kind of just want it to look like, I don't know, almost like uniformly spread out. Maybe uniform is not the right word, but just you definitely don't want to see see patterns. So I think like when we've had the standardized residual plot over something like this with the square root transform, where you just kind of see it like all over the place. This is ideal, okay? And what we're seeing here is, you know, I think the circles kind of obscure it, but we see a few very significant outliers, which indicates a problem, right? Because this means this is 6 standard deviations away from the mean, which shouldn't really happen, okay? So we're expecting most kind of to be between, you know, 2 and -2, or, you know, 3, you know, in extreme cases, and we're kind of expecting them to be spread out. And it seems to be there's some kind of a little bit of a dip here also, okay? So I think it'd be more clear on maybe a better plot. Okay, so the book talks about transforming one at a time or both at the same time. Okay, and there's a function called BC trans, and I'll make sure to find have the code appropriately printed in the R Markdown file when I post it. So this would be Boxcock transformation, and you apply it. Okay, and then so when you fit the transformation and you get the output, it estimates the appropriate power transformation that we should be using, okay? And it also kind of provides some extra statistics, right? The standard error and the score and things like that. And so, you know, you can use these directly as is. A lot of times, and you might have people with different opinions, but you know, we might choose to use nice round numbers like 0, okay, for this one, which corresponds to a log transformation, and 0.5, which corresponds to a square root transformation, just because those are a little bit easier to grasp conceptually. There's no rule that says you have to do that, but I think a lot of people prefer to do that just because it's easier to conceptualize. Even if we have a hard time understanding what exactly a log transformation means, versus, you know, if we transform y on the log and transform x on the square root, what does that mean? You know, that might be a tough interpretation still, but just for the sake of clarity and easiness, we might apply that transformation. Okay, so basically, it's just a matter of doing the appropriate transformation, and then you refit the data, okay? And so here, we transformed score into the square root of score, and we transformed max salary to the log of max salary using that power transformation. And this seems to be a lot more better behaved, okay? Yes?
How is minus 0.09
The same as 0?
or lead us to do the log transformation?
So remember that, so this is our estimates of lambda.
Right.
Okay, and so this, we say this is pretty close to lambda being 0, and lambda 0 is the log transformation. So when you have So going back to, where did it go? Okay, this thing.
Oh, right.
Yeah. Oh, wait. Yeah. That as lambda approaches 0, the limit of this thing when lambda goes to 0 is the log of that. That's all. Okay. So so we do that, and we say, hey, it looks good, and then we do our diagnostics, and we say, okay, yeah, that looks close to normal, and then the square root of the score, that also looks close to normal. So that seems to have done the transformation well. And then when we look at the diagnostic plots, and we look at the standardized residual and the scale location, and again, these plots probably aren't the best plots, but we say, okay, this, that one outlier that was crazy at 6 standard deviations has kind of been brought under control to around 3, which is a good sign. And then the scale location plot, we see a tiny bit of a little bit of a slope, but it's a lot better than what we had before. Okay, and so we take this and we say, okay, sure, this seems to be better, basically. Okay. And so the book talks about you can use BC transform to do them both at the same time, and then it also talks about using the transform to do one at a time. To be honest, I don't know. I don't think there's any advantage to doing one first and then the other versus doing them both simultaneously. So I'll try to see if I find any reasons as to why, but yeah. So I'll make sure to get all of the code and kind of comment on the process there. But that's pretty much it. And again, it's an imprecise science in that you get data, you say there's some problems with it, you try a few transformations, maybe that fixes your problems. Okay. Maybe it doesn't, all right? And sometimes the answer is your model is just flat out wrong. You're using the wrong predictor, okay? And no matter what you try to do to transform your data and transform your predictors, you're not going to get a model that works because it's a bad model, okay? And so sometimes that also happens. So, be open about this. I think there is a potential for abuse in that you don't want to fit every single possible model just so you can kind of get one that is slightly statistically significant, okay? So you don't want to what's called p-hack, in that you're just trying to fit all of these crazy different things just to say, hey, this one's kind of significant, all right? All of this transformation stuff is with the perspective of I'm trying to fix some problems in my data, not trying to prove a point here. Okay, so, but yeah, these are just tools that you can use to try to fix the problem. Sometimes they succeed, sometimes they don't, and be ready for that. Okay. All right, we'll end there, and I'll see you guys on